Welcome to lecture number 36. Today we are going to discuss Excimer and Exciplex. So, in some case what has been seen is the fluorescence intensity, right, is actually keep on changing with the increase in the concentration. You can say that fluorescence intensity is decreasing by increasing the concentration of the fluorophore is maybe because of the inner filter effect or front surface absorption that I have already discussed. But in this case what has been seen is that while the fluorescence of one region is decreasing, the fluorescence in other region is increasing itself. It means that the one part of the emission spectra, if you just follow, it looks like a fluorescence is quenching, but in some other part the fluorescence is actually increasing as a function of the concentration. Let me show you a specific example, then it will be clear to you. If you take this molecule, this is the most famous example. This is pyrene in N-heptane. If you look at the emission spectrum of pyrene in N-heptane, when the concentration is not very high, what you are going to see is something like this. Right. Let us say the concentration is about 10 to the power minus 6 molar. Now, as you increase the concentration of this pyrene, right, you will see initially obviously the fluorescence intensity will increase, right. Let us say for example, if from 10 to the power minus 6 I make it as 2 into 10 to the power minus 6, right. So, then obviously we will going to see the intensity will increase like this. So, here is 2 into 10 to the power minus 6. But if you increase more, so for example, about a millimolar, then what you will see such kind of emission. This is for the 10 to the power minus 3 molar. That means, what you can see here is the quenching of the band, and is the new type of emission actually comes into picture. Here this new type of emission, what you can see over here is explained on behalf of this excimer formation. Right. To explain this, let me take the ground state and the excited state of this pyrene molecule. Right. So, let us say this is my HOMO and LUMO of this pyrene monomer, one pyrene molecule, and in the ground state both the electrons are in the LUMO, right. And you have another pyrene, let us say this is my pyrene, this is my pyrene, and in another pyrene is also in the ground state, both the electrons are occupied in the LUMO, right. Now, consider that these two pyrene molecule actually interacting with each other, right. So, then their orbital will mix up and I will get a completely different molecular orbital. So, for example, if I now consider that these two these are the itself molecular orbital, right, homolumo, and they interact and they form another set of orbital, and these two interact and create another set of orbital. This one is for pyridine pyridine, but here in this case both the pyridines are in the ground state. So, this will be occupied 2 electron, this will be occupied by the 2 electron. So, this is the case of ground state. However, in the excited state, if you look at, let us say these are the my pyridine, this is one pyridine, sorry, but this pyridine molecule is not in the ground state, this is in the excited state. So, I have one electron over here and I have another electron over here, right, and here this pyridine molecule is in the ground state. So, if I now consider pyridine one in the excited state and another in the ground state, then what I will going to see in the mixed orbit, in this case 2 electron will come here and 1 electron will go there, and in this case 1 electron will come here. Now, if we just look at here, in this case, let me change this one, look at this one, 2 electrons destabilized. If I write this destabilization as unity for per electron. So, these 2 electrons destabilized. If I just write a unity 1 for the destabilization or stabilization, then this is -2 because of the 2 electron, and here 2 electrons stabilized, 2 electrons stabilized. So, I can write +2 in this case, and here net stabilization is equal to 0, +2 and -2 equal to 0. However, in this case you see here 1 electron stabilized. So, I will write here +1, here 1 electron destabilized, right. So, I will write -1 and this one 2 electrons stabilized. So, I will write here +2. So, the net stabilization is there. So, I have a net stabilization. Right. So, I am going to have a net stabilization. Net stabilization is +2 and then I have 2 electron. So, per electron net stabilization is +1. So, I am going to have this net stabilization only when this pyridine one of them is in the excited state. Now, if you consider the repulsion term, right, here I have not considered the repulsion term, then if I now draw the potential energy surface for as a function of the pyridine distance, then I can simply draw this, right. Let us say this is my ground state, I am starting from a distance over here, where I consider that one pyridine and another pyridine, they are far apart, and this distance is actually decreasing So, in the x axis what is there? The pyrene distance. As the two pyrene will come close, right, then this energy must increase because of this repulsion, right. This electron of this pyrene, this electron of that pyrene, they will repel each other. But when I have this pyrene in the excited state, so this is in the ground state, right, potential energy surface of the two pyrene. Now, when I have this excited state, obviously one of the pyrene is in the excited state. So, total energy must be more, right. Here is my one pyrene is in the ground state, another pyrene is in the excited state. So, here I will write P y plus P y, and here is my P y star and P y. So, because of this net stabilization, I showed here this net stabilization, right. When these two pyrene will approach, at some point of time there must be some dip, and then obviously this repulsion, because of this repulsion term, this will increase. Okay. So, my drawing is not very good. I should have drawn this like this way, like this. So, this is the correct version. Now, you look here, this pyrene obviously will have its corresponding vibrational level. When I am drawing at this end of this diagram, it means the two pyrenes are not interacted with each other, they are far apart, right. So, during any transition, like when you are exciting, so this excitation will be either from here to here according to the Frank-Condon principle, like here to here, here to here. So, those vibrational fine structures are very nicely visible in case of pyrene. When pyrene will relax back from the excited state to the ground state, then emission will start from here, and then it can come from here to here, from here to here, here to here, right. So, then the vibrational fine structures are visible, right, in case of pyrene. However, when this pyrene distance decreased, right, you come up with this stage, right, the immediate ground state, right, is not stable at all. Once it will form, immediately they will break, right. And in this case, when this pyrene star and pyrene will come from this excited state to the ground state, you will not be able to see such kind of vibrational fine structure. Moreover, you see the energy gap here, this gap is less than this gap. That means, this emission will be red shifted, and exactly what you can see here in case of pyrene, the at a low concentration the emission is like this, and in the high concentration this is low concentration, and in the high concentration this part decreased and new part increased. So, this is high concentration. Now, if this phenomena, right, is happening between two pyrene molecule, right, such phenomena is called the excimer, because this is kind of a dimer formation. Although I have not discussed the dimerization in the ground state because of this nature of this course, but I would like to tell at this point that in ground state some molecules are prone for the dimer formation, and because of the dimer formation, I mean you can see that change in the absorption peak of a molecule. For a H type dimer, the absorption peak is typically get blue shifted, and for the H type dimer means sandwich type dimer. One molecule is forming a dimer with another molecule like this way, right. Then you will get absorption spectra blue shifted, and in J type dimer one molecule is getting dimerized with other molecule like this way, head to tail fashion, and you will get the absorption spectra red shifted. In this case, what you can see that this dimer formation in the ground state is not visible, right, because if you look at this concentration dependent absorption spectra of the, because this is my fluorescence intensity of fluorescence, and here is your lambda emission, right. But if you look at this absorption spectra of this molecule, you will not see any change in the absorption spectra. That means, this dimer formation is not happening at the ground state of this molecule, and that is what you have seen right in this normal case, that they are repelling, right, it is not stable. But in the excited state, this dimer formation is visible, right. So, that is why it is called the excited state dimer or excimer. So, such kind of phenomena is known as excimer, right. So, basically what I have defined, this AM, some molecule AM in the excited state is interacting with another AM which is in the ground state to form AM star AM, right, and this is known as my excimer. Sometimes it is also possible that one of these molecule which is in the excited state AM star is actually interacting with a different types of molecule, right, not N, but again this interaction is favorable, which will leads to the formation of M star N, right. So, this is not a dimer, see, because here AM and here is my N. So, they are not same, and this type of case is known as this type of complex formation, right, complex formation between M and N, but these complex is formed only in the excited state. So, this is known as Exciplex. So, you have Excimer, Exciplex, the mechanism is more or less very similar, right. Now, there are few things one can discuss on this Excimer or Exciplex formation, but let me discuss with the time resolved study of Excimer and Exciplex, right. Obviously, this Excimer formation, let me talk about this Excimer. Obviously, this Excimer formation cannot be instantaneous. That means, you have to excite your molecule, right. M is now excited to M star, then M star will interact with M, and then there will be a formation of Excimer. Obviously, it is not instantaneous, it will take some time, right. That time taken for the Excimer formation can be easily visualized if you do the time resolved measurement. If you remember, as I told you that let us say this is your emission spectra as I showed over here, when at the high concentration. So, this is my high concentration, the emission spectra is something like this as I showed. Now, if you monitor the fluorescence transient at different wavelengths, let us say at this wavelength, this and many such kind of wavelengths till here, right. You have measured the different wavelengths. So, and the functional form of these different wavelengths are let us say AI e to the power minus t by tau I sum over I. Depending on your system, it could be I equal to 1 and 2, or it could be a 1, 2, 3, that means it is maybe single exponential, bi exponential, triple exponential, and so on and so forth, right. Now, with the help of this steady state intensity, you have this with at your hand measured, and you also have steady state intensity as a function of lambda. This is at for a particular lambda, right. this also at your hand. So, from there you can easily determine the time resolved emission spectra, right, and that you remember I told you intensity is a function of lambda and time, right. So, this is equal to I steady state divided by sum over A I tau I into sum over A I e to the power minus t by tau I, right. So, this is obviously a particular lambda I am talking about, and this is my time profile. So, with this at a different time you can actually capture how the emission spectra looks like at a given concentration, but that emission spectrum is at different time. Soon after the formation, soon after the excitation, obviously the emission spectra will be more monomer like, right. This is my monomer, here is my monomer, and this is my excimer. So, if you do a time resolved studies and then reconstruct the time resolved emission spectrum, then what you will see at early time the emission spectrum will be something like this. And as time goes, this emission spectrum, so this is time t equal to 0, and after some time you will see little bit has formed, time t equal to t, and at time t equal to infinity probably what you will going to see is such kind of thing, right. So, from here you will be able to calculate the evolution of this band with time, and you can talk about the formation kinetics, right. Like previously, as I have shown this excited state proton transfer, right, I can even model it without any problem. Let us say this is my molecule which is undergoing the Excimer formation, the 2A are present over here, and I am exciting with h nu, that is the suitable wavelength for the excitation, and I am exciting this to A star, one of them, right, another is like this A, and then there is a formation of, obviously this can break. So, I will write this rate constant as a k Excimer formation, k Excimer dissociation E d, which will form A star A, and it has its own radiative rate constant. So, I have its k r, it has its own k n r, right. So, with this k r it will form A plus h nu, and with this k n r it will form only A, right. So, then you are back to the previous case here A and A, right, and the Excimer also can come back to the ground state. Let us say this is for the Excimer fluorescence. So, I will write this as k E f, and it will produce 2A plus h nu prime, because this wavelength is different than this wavelength, and it can also undergo some non-radiative pathway, and let us name it as k E q, right, which will form 2A, but no light. Now, you see such kind of kinetic model is very complicated kinetic model, and but it is possible to solve with some assumption here and there, and basically if you take this photostationary state assumption, then we will be able to solve such kind of model. And under photostationary state assumption, what you can do, you can try to find out that the formation of this A star A, right, is kinetics, and the other dependency on the formation of A star A, right. But I am not going to write all those expression here, because it is not necessary at this point of time, but as I told you that this Excimer and Exciplex are the excited state phenomena, and in such cases, right, what you are going to see is the formation of a new emission band, which is much broad and red shifted compared to the monomer emission band. So, we will finish our discussion on Excimer and Exciplex here, and we will continue our discussion in the next lecture. Thank you very much.